Today let us learn about how to draw the ray diagram to locate the image formation in convex lens as well as in concave lens. So first we will do the case of convex lens. So in convex lens there are many situations where the object can be placed. Okay, so we will be doing different position of objects, and we will see where the image is formed, and we will also see what type of image, the characteristics of image, etc. So let's start with the image formation ray diagram, how to draw the ray diagram. So when you are drawing the ray diagram, the first thing to keep in mind is, the first step to draw the ray diagram is you have to draw the principal axis. So you draw a straight line to show the principal axis, and you can name the principal axis as maybe PQ. Okay, so that is the first step. Now the second step of drawing the ray diagram is you mark a point O anywhere between P and Q, and that O will be the optic center or the geometric center of the lens which we are going to draw. Now through the optic center perpendicular to the line PQ, you mark a dotted reference line to show the refraction or refracting surface. So that is actually the line which is passing through the geometric center of the lens. After drawing that reference line, you draw the lens. So here I am going to draw a convex lens. So you draw a convex lens there. Okay, so you have to draw a convex lens. So O is the midpoint or the optic center of the convex lens that we have drawn. After drawing the convex lens, you have to take equal measurement from O, the point O, towards left and right. Okay, so you take equal measurement and you mark the focal point F1 on left and F2 on the right side. So the F1 should be OF1 should be equal to OF2, that is focal points on both the sides should be equidistant. After writing focal points, you take double the focal length, that is 2F1. So you have to measure double distance, that is you take OF1, take the double distance and mark 2F1. Similar way on the other side you have to mark 2F2, that is double the distance of focal length. So this is the first step. Now after drawing the preliminary setup, we will take each case in detail. So first case which we are going to do is, let us take the first case as case 1, when object is at infinity. So we have to place the object at infinity. So you know, for infinity position we need to keep, or we need to consider parallel ray. Okay, so we have to consider two rays. You know that for image formation, in the last video I have told you that in order to draw the ray diagram we need at least two rays, minimum two rays. Okay, so we have to take two parallel rays. So for our convenience, one of the ray which I am going to take is a ray which is passing through optic center, because you know that when the ray is passing through optic center there won't be any deviation or there won't be any refraction. So I am going to take a ray which is passing through optic center, so that it will be convenient for us to. So this is the ray which is passing through optic center, and when we consider the ray which is passing through optic center, that ray don't have any refraction. Always remember, when you are showing the rays, you need to show the arrow marks indicating the direction of the incident ray as well as the refracted ray. Okay, so the arrow mark should be shown for the incident ray as well as refracted ray. So you got the first ray. Now the second ray, here I am going to consider the ray which is passing through focus, okay, and which is parallel to the first ray, because we need parallel ray for infinite case. So here I will draw a ray which is passing through focus and which is parallel to the first ray which we considered. Okay, so this is a parallel ray which is passing through focus. So you know that if a parallel ray passing through focus, or if a ray passing through focus after refraction through a convex lens, it will go parallel to the principal axis. So after refraction, what will happen? The refracted ray will go parallel to the principal axis. So here also incident ray arrow should be shown. If arrow is not there, you won't get any marks, because the direction of incident ray and refracted ray are important. So after refraction, the ray will go parallel. So like this. So parallel ray should be shown. Okay. Now if you consider the interaction, or if you consider intersection of these two rays, that is incident ray, the two refracted ray, you can see the point of intersection is this point. Okay, so the point of intersection of those two refracted ray will be giving us the image. So the position of the image is the point of intersection of the two refracted rays. So I have shown it using yellow color. So here I get the image, and if you note down the position of the image, you could see that the image is falling on the focus. Okay, so you got an image which is at the focus, and if you consider the size of the image, you will see that the size of the image will be small, very small. And if you find the position, or whether the image is erect or inverted, you could see that the image is inverted. So when you write the characteristics, so let's write the characteristics. Characteristics of image. In the first case, that is when object is at infinity, you find that the image is a real image. So real image means the image formed is due to the actual intersection or actual meeting of two refracted rays. Then second point is it is inverted. And the third point is it is highly diminished. It is very much small compared to the object. Okay, so these are the characteristics of image that we get when the object is at infinity. Now when you consider the uses of such position, you can use this position of object in camera. That is, suppose we are an object is at infinity, the image will be formed at the focus. Okay, so this position can be used in camera for focusing. Then another use is used in burning glass. That is, suppose you know the ray from the sun, it is a ray coming from infinity, and it can be concentrated or converged to a single point at the focus. And if you place certain things, or if you place any paper or something for a long time, you will see that the paper will start burning. So you can concentrate the ray of sun or heat on a particular point, that which is the focal point, for getting heat or for burning purpose. Okay, so the two uses are, it can be used in camera, also it can be used as in burning glass. Conclude, we can say, when object is at infinity, image will be formed at focus on the other side of the lens, and the characteristics of the image which is formed, the image will be real, it will be inverted, and it will be highly diminished. And the important use of this particular position is it is used in camera and also used in burning glass. Now we will see the second case in which object is placed beyond 2f. So it is not at infinity, but it is far away from the lens. So that's why a position beyond 2f is taken. So here I have shown the primary setup of the lens. As I told earlier, we need to draw a principal axis PQ, then the reference line using dotted line. Then you have to mark a point O, which is the optic center. Then take equal measurements on either side as f1 and f2. Also take 2f1 and f2 as we did in the previous case. So when object is at beyond 2f1, you have to keep an object just before 2f1. So I am going to place the object here, which is beyond 2f1. Now in order to form the ray diagram, we need two rays. As we did earlier, we will take one of the ray which is passing through the optic center so that it goes undeviated, and it is very convenient to get the ray diagram. So the first ray I have shown here. So it is the ray which is passing through the optic center, which is moving undeviated, and I have shown the direction of incident ray as well as the refracted ray using arrow marks. Now second ray which I am going to consider is a ray which is parallel to the principal axis. So a parallel ray parallel to principal axis will go through the focus after refraction. Okay, now let us see that ray as the second ray. So this is the second ray which we are going to consider, which is parallel to principal axis. So after refraction, you know, it will go, it will pass through the focus. Now let us see the refracted ray. So here I have shown the refracted ray. So parallel ray after refraction will pass through the focus. Okay, now if you consider the meeting of two refracted rays. So this is the first refracted ray and this is the second refracted ray. You could see that both the refracted ray is meeting at a single point, which is this point. So that is the meeting point, and it is the position where we get the image. Okay, so there you can draw the image. So when you see the position of the image, you could see that I didn't give name for the object. Object is AB and image is A dash B dash. Okay, and you can see that the image is inverted, and the position of the image, you could see that it is between f2 and 2f2. That is, the image is between second focal point and double the second focal point. So you can write the position of the image here as image between f2 and 2f2. So that is the position of the image, and it is on the other opposite side of the lens. Now if you take the characteristics of the image, you could see that. So when you look at the characteristics of the image, you can see that the image is real. Real means the image is formed by the actual meeting of the refracted ray, and it is inverted. Okay, so the image is inverted, A dash B dash is inverted, and it is diminished. It is not highly diminished, but the size of the image will be small compared to the size of the object. So that is the characteristics of the image. Now we will see some uses of this position. So this type of or this position of the object is also used in camera. That is, when the object is not too far, we can make use of this position in camera. So that is the use of this position of object in convex lens. Now we will see the case 3, that is when the object is placed at double the focal length, that is at 2f. So here the object is shown as AB. Now for drawing ray diagram, we need two rays. So first ray anyway will take one which is passing through the optic center. First ray which is moving through the optic center is shown here. So, since it is moving through the optic center, it don't have any deviation. Arrow mark for the incident ray and the refracted ray is also shown. Now second ray, we will take a ray which is parallel to principal axis and which is moving to the focal point. Second ray is also shown here, ray parallel to principal axis. After refraction it will pass through focus. Now the first refracted ray and the second refracted ray, they will meet at a point where we get the image. So it can be seen that the meeting point of those two refracted ray is at 2f. So we will be getting image at 2f. That is, when object is placed at 2f1, we will get the image at 2f2. So now we will draw the image. So when you are drawing the image, you can see that the image will be inverted. This is an erect object, so we get an inverted image. So the inverted image can be drawn here. Okay, and you can name the image to be A dash, B dash, A dash and B dash. And when you look at the size of the image, you can see that the size of the image is same as that of the size of the object. If you measure, you will see that size of image is same as that of size of the object. So the image which we got is at 2f. Then it is inverted, it is real because it is formed by the actual meeting of two refracted rays. So it is a real image, inverted image, and having size same as that of the object. So we will write the characteristics. So the position and characteristics of the image is given here. Image is at 2f on the other side of the lens, and the characteristics, it is a real, inverted and same size as that of the object. Now we will see the fourth case in which the image object is placed between 2f and f1. So we are moving from infinity towards the lens. The object is the position of the object is changed from infinity towards the lens. Now we reached 2f. Now we will place the object in between 2f and f1. So we will see what will be the position and characteristics of the image we get. Now we will move to case 4, when object is placed between 2f1 and f1. So here the object is placed between 2f1 and f1. Here also we will consider the name of the object is given to be AB. It is represented by this green arrow. Now we will take, as usual, we will take the first ray which is passing through optic center and the second ray parallel to principal axis. The first ray is the one which is passing through optic center, which is going undeviated. Show the arrow mark for the incident ray as well as the refracted ray. So the second ray is the parallel ray, parallel to principal axis. Ray after refraction is going through focus. So here the two refracted ray will meet at this particular point where we get the image. Now you can see that this point is beyond 2f2. So we are getting the image beyond 2f2 if we are placing the object between 2f1 and f1. Okay, now we will draw the image. So drawing the image, you can draw here. You could see that the image is actually larger than the object. So A dash, B dash, image is inverted, and the size of the image, when you compare the size of the image with that of object, the image is enlarged and position is beyond 2f2. So we can write the position and characteristics of the image. So the position of the image is beyond 2f2 as mentioned earlier. Characteristics involves it is a real image because it is formed by the actual meeting of two refracted rays. It is an inverted image, that is A dash B dash is an inverted image, and it is magnified, means the size of the image is larger than that of the object. Now this position of object in convex lens can be used in slide projectors or in cinema projectors. So there the object will be placed between the focal point and double the focal point of the projecting lens or the projector, and we get it on the screen, which is placed at a distance which is beyond 2f2, so that we get a magnified image which is inverted in nature. So it can be made erect using certain other techniques, or you can place the slide in an inverted position so that you get a exact image of the object. Next position is the one in which the object is placed at the focal point, first focal point f1. So let's see how the image is formed. First we have to take a ray which is passing through the optic center, and the other one which is passing through parallel to the principal axis and passing through the focus. So this is the ray which is passing through the optic center, which goes undeviated. Now the second ray is the parallel ray parallel to principal axis. So here when we draw the second ray, you can see that the refracted rays, the first refracted ray and the second refracted ray, both are going parallel to each other, so that the image will be formed at infinity. So this is moving towards infinity. So we can say that the image formed is at infinity. The position of the image is at infinity if we place an object at focal point f1. So you can write image is at infinity. Or we can say that image is formed at a very large distance. Now we will see the characteristics of the image form. So the characteristics of the image is real, it is inverted, and it will be highly magnified. Okay, now this type of or this position of image can be used in collimator of spectrometer, that is where we need to get a parallel ray. In certain cases, in certain experiments and all, we need parallel ray of light. So in such cases, this position can be made use of. That is, you have to place a source of light at a focal point in front of the lens, so that the ray which is coming out will be parallel ray, which can be used for doing certain experiments and all. So it is mainly used in collimator in spectrometer. Now we will see the last case of convex lens, that is when we place the object, that is we reached focal point now. Now we are going to place the object between focal point and optic center, that is very near to the lens. Now the last position of the image for convex lens image formation is object is placed near to the lens, that is between focal point and the optic center. So here also we consider two rays, one passing through optic center, the other one which is parallel to principal axis. So this is the ray which is passing through optic center, which goes undeviated. Now the second ray. So the second ray is the ray which is parallel to the principal axis. After refraction, it moves towards the, or it goes through the focal point. Now here you can see that there is no possibility of these two refracted rays to meet. Okay, so they won't meet at any point. So what we have to do is, so this is actually a divergent ray, it is not a convergent ray. So we need to back trace the refracted rays. Okay, we have to trace back the refracted ray to get the position of the image. When you are back tracing, always you have to do the back tracing using dotted lines, not using solid lines. You have to use dotted line for back tracing. Now let us see where the image is formed by back tracing the refracted rays. So when you are back tracing, you can see that these two rays they will meet, appear to meet or appear to come from this single point where we are going to get the image. So if you draw the image, you know that since it is not due to the actual meeting of the refracted ray, the image formed will be a virtual image, and the image which is virtual should be always drawn using dotted line. So the image should be drawn as dotted line, and you can see that it is on top of the principal axis, so the image is erect. So, and when you see the position of the image, you can see that the position of the image is on the same side as that of the object, but it is behind the object. Okay, it is behind the object on the same side as that of object. So that is the image formation when the object is placed at the focus. So the characteristics of the image which we get are, it is virtual in nature, erect in nature, and magnified compared to the object, and such position can be used for in simple microscope, or maybe in magnifying glass, reading lens, etc. This position of object is made use. So we have seen all the ray diagram construction of different position of object for the convex lens. 6 cases are there. Only one case, that is this last case, is giving us a virtual image. All the other cases are giving real image, and we found how the size of the image is differing with respect to object in all the cases, and also we have seen the uses. Now we'll see about the ray diagram formation in case of concave lens in the next class. Compared to convex lens, only less position of objects are there for concave lens. Only 2 positions are there for concave lens, that we'll see in the next class.